So in the last lecture we talked about inverse of a matrix, and you remember that if you have an n by n matrix given by, then you remember its inverse was equal to 1 over determinant of this matrix multiplied by another matrix which is obtained from the cofactors, and here is C11 up to C1n. So whereCij's are the cofactors, remember. This is the inverse of matrix. However, this is not the procedure to calculate the inverse because it involves a lot of computations, and therefore we shall talk about another method which is utilized to compute inverse of matrices. So this method is called Gauss Jordan method. The concept is, or the approach is, you construct this matrix. If you want to find the inverse of a matrix A, then you construct another matrix. That is, with this matrix you augment an identity matrix and then apply elementary row operations such that this matrix is transformed into this matrix. Here becomes identity matrix, and here when you apply the row operations, this will become something else, and let's call it K. Then this K is a matrix, then A inverse will be equal to this K. The procedure, you augment an identity matrix. The dimension of this matrix is n by n. You augment an identity matrix of size n by n, and then perform elementary row operations to transform this augmented matrix into this form. That is, instead of A, you get identity matrix over here, and then this will become something else, another matrix. Let's call it K. Then A inverse is equal to K. So before we address the question how it is equal to A, let's first apply it to some particular example to determine the inverse. The question is still there, why this procedure gives you inverse of that matrix. That question is still there. We shall address that question. So you have this matrix, and for this matrix you append an identity matrix over here. We shall perform elementary row operations such that this matrix will become the identity matrix. So for that purpose, what we can do, we can simply multiply first row with -1, for example. So let's do some steps over here. So here it will become +1, -1, -2, and -1. You can multiply any row by a non-zero constant. So we have multiplied first row by -1. Now we can add a scalar multiple of first row with this third row, and another scalar multiple of first row with this row. So what do you get then? So perform the operations to transform this matrix into identity matrix. You can do that, so please do it. And then multiply this row by, of course these operations are not unique. I have performed these operations. Some of you will like to perform some other elementary row operations. This is not unique. So what else? How we can further proceed further? We divide this row with 2. So what do we get over here then? Dividing this row by 2, we have 1 over here and 7 by 2. Here is 3 by 2, 1 by 2. Then divide this row with minus 5. So what you get? 1 and 4 by 5, 1 by 5 and minus 1 by 5. Then multiply this third row with 7 by 2 or minus 7 by 2 and add it to the second row. And multiply this row with 2 and add it with the first row. So what we are going to do is R1 plus 2R2, 2R3. So 1 minus 1, we have limited space, so 1 minus 1, 0, and minus 1 plus 8 by 5, minus 1 plus 8 by 5, so minus 5 by 5, it is 3 by 5, minus 2 by 5 over here. So each of you would have some different elementary row operations. It is not mandatory to make these row operations. And then R2 minus 7 by 2, R3. So you will add these two rows and get something over here that will be inverse of the matrix. By hand calculations, this procedure is generally difficult compared to the earlier procedure. However, for computers, this procedure involves less multiplications, less arithmetic operations. Therefore, this is much easier and less costly as far as number of computations is involved. So you can perform all the three elementary row operations, whichever you want. You want to multiply a row by a non-zero constant, you can do that. However, you have to multiply the entire row of this augmented matrix. Yes? So there is a question whether we can perform column operations or not. So the answer lies in our first question, that is why this procedure gives us inverse of that particular matrix. So let's first address that question. Is there any other confusion regarding the procedure? Procedure, although involves some computations, however, the concept is quite clear. You perform elementary row operations on this augmented matrix such that this matrix is finally transformed into identity matrix. Then whatever we get over here, that will be the inverse of that particular matrix. So the question is how this procedure gives us inverse of that particular system matrix, that particular matrix. So yes, exam point of view से आप पूछ रहे हैं तो procedure is important. Of course, अगर जिस student ने procedure भी सही किया है और computation भी सही की है, तो he will get more marks. लेकिन जिसका procedure ठीक है, लेकिन computational mistakes हैं, तो उसको भी कुछ number points तो मिलेंगे. So now here is the question that why this procedure gives us inverse of a matrix. So you are familiar with system of equations. can you find the solution to this system of equation where E1 is the first column of identity matrix? How would you find it? So you will construct an augmented matrix from this matrix and the right hand side, and then perform row operations to reduce it into echelon form. Can you also find the solution to, let's write it x1 over here, this is vector x1. Can you also find the solution to this system of equations where E2 is the second column of this identity matrix? Again, the same procedure, construct the augmented matrix, and similarly AXN, this XN is a vector, and the nth column of this identity matrix. Again, the procedure is the same. You construct augmented matrix. So why not to, if we want to solve these different system of equations, then why not to do all these steps in a single way? That is, to solve this system of equation, you are making this augmented matrix E1 over here, and then performed row operations. To solve this system of equation, why not to write it over here, and similarly over here, and perform the row operations for all these equations for once, right? So इनका सर ऐसे ऐसे हिलता है, तो इनका मतलब ये होता है कि इनको समझ आ गई है, अभी मुझे डिकोड मैंने कर लिया है, तो ऐसे ऐसे सर हिलने का मतलब थोड़ा सा मैं कंफ्यूज हो जाता हूँ, लेकिन अभी मैंने डिकोड कर लिया है कि इसका मतलब है कि समझ आ गई है. So we have these system of equations, and we want to solve this thing. So we have performed row operations for all these system of equations for once, and then you have this thing over here. You have we have just collected them together to write it this complete identity matrix, and then performed. So to solve the system of equations, you are allowed to perform row operations. You performed row operations to transform this into this form. So what do you get from here? The solution of which equations? If I collect the columns over here, x1, x2, xn up to, so what is this thing, this system of equation? A multiplied by x, where what is this capital X? These x1, x2, xn are the columns of this matrix, and solved it. Solved it, performed elementary row operations such that this came out to be equal to k. So what is x in this case? K. What was x? If x satisfies this equation, then x is the inverse of A. If x satisfies this equation, then x is inverse of A. And here we have found this thing. Therefore, this procedure gives us the inverse of that matrix, right? So we wanted to find this inverse x. We have formulated it into system of equations, performed row operations to transform this thing. This equation, these equations are the same, this thing, and therefore x is computed, and therefore this procedure gives you inverse of a matrix. Is it clear? So there was a question over here. Are we allowed to perform column operations over here to transform this matrix to identity matrix? Can we perform column operations? You remember here we were not allowed to perform. Here if we had this system of equations, we had constructed this augmented matrix and we were not allowed to perform column operations. So here again you are not allowed to perform column operations. There is one strategy, in that way you can also perform column operations, but just if you want to follow this procedure, you are not allowed to do that. Here we were not allowed to do that, right? What is inverse of a diagonal matrix? So if A is a diagonal matrix, non-zero entries on the diagonal only, other entries are 0. So inverse of this matrix exists if all of these diagonal entries, these are non-zero. If all of them are non-zero, then only then inverse exists for this matrix. And the inverse of this matrix is given by A inverse of a diagonal matrix is 1 over A11, 1 over A22, up to 1 over ANN, and all other entries 0. So can you prove this statement, or you just believe it without any proof? So proof of this statement is very simple. So there are different ways to prove this thing. You know that inverse of this matrix is given by, what is determinant of A? So determinant of A is the product of these entries on the diagonal. We know for triangular matrix, the determinant is the product of entries on the diagonal. And what is C11? C11 is obtained by determinant of a matrix, which is obtained by omitting first row and first column. So what is that? A22, A33 multiplied by ANN. And what are these things? For example, C12. C12, how do we obtain? So C12 is obtained by omitting first row and second column. If we omit first row and second column, here there will be a 0, right? This C12 will be determinant of this thing, 0, and A22 over here and ANN over here. So all other entries 0. So 0 multiplied by something is equal to 0. C12 is equal to 0. Similarly, C1n, this is also equal to 0. You can compute the rest as well in a similar way. You will find that C22 is equal to, what is C22? A11, A33 up to ANN, and all other entries over here will be 0. So therefore this inverse is C11 divided by this determinant, this entry over here, that is this thing, whole divided by determinant, that comes out to be equal to 1 over A11. Similarly, here the entry is C22 divided by this determinant, which comes out to be 1 over A22, and so on. Hence, this is the inverse of a diagonal matrix. So there are multiple ways to prove the same thing. So here is one more suggestion, and that is also very good suggestion. That is, why not to do it like this one? Construct the augmented matrix and then divide the first row of this matrix with A11. We shall have this matrix over here. So here will be 1, 0, 0, and here the entry will be 1 over A11. And similarly, divide the second row with A22. So that is also an easier way to prove the thing. So some properties of inverse of matrices. If you have two matrices A and C, then inverse is equal to C inverse A inverse. Please prove this statement. These are n by n matrices and their inverses exist. Then prove this statement. So here is a hint. A multiplied by C multiplied by AC inverse. What is that? Identity matrix. How to proceed? Any suggestion? Multiply it with A inverse, both sides of the equation. A inverse. So A inverse multiplied by identity matrix, that is equal to A inverse. And A inverse multiplied by A, that is equal to identity matrix, and identity matrix into some another matrix is the same matrix. So here is A inverse. And then multiply it by C inverse, both the sides, C inverse. Remember that matrix multiplication in general is not commutative. That is, if you have two matrix BA, AB, that is not in general equal to BA. So if you are multiplying this matrix from the left by another matrix, you have to multiply this matrix from the left as well, right? So hence we have proved that particular statement, that is AC whole inverse is equal to C inverse into A inverse. In general, you have if you have more matrices, that is A multiplied by C multiplied by other matrices multiplied by P multiplied by Q whole inverse. What is that equal to? Q inverse, P inverse, and up to C inverse and A inverse. That is the inverse of a matrix. What is this thing? A inverse, whole inverse, that is A. And again, proof of this statement is very simple. You can prove this statement that A inverse, whole inverse, that is equal to A. You can prove it. So here is a theorem which gives which describes some properties of matrices. If you have matrices A, B, and C are n by n matrices, these are n by n matrices, then this statement of the theorem is in general this statement is not true. AB equal to AC does not imply that B is equal to C. However, if A is full rank, then this statement implies this statement. In general, you cannot give this statement. However, if rank of A is equal to n, then this thing implies this one. So how to prove it? Please prove this statement. Pre-multiply it by A inverse. So we have both the sides of equation, A inverse B, A inverse into A, C. So this implies that B is equal to C. This is only true when inverse of A exists. So inverse of A will exist if rank of A is equal to n. We have learned it. So if rank of A is not equal to n, then you cannot give this statement, right? So if rank of A is equal to n, then A multiplied by B, if this is equal to 0, it implies that B is equal to 0. In general, again this statement was not true. However, if rank of this matrix A is equal to n, then this statement is true. Again, this can be proved in a similar way. Multiply both sides with inverse, so B will come out to be equal to 0 matrix. What is a singular matrix? So if rank of this matrix is equal to n, if rank of A is equal to n, then it is called non-singular. Another way to write it is that the determinant of, if determinant of A is non-zero, then this matrix is called non-singular. And if a rank of A, an n by n matrix A, that is less than n, then it is called singular. So if rank is equal to n, then inverse of that matrix will exist, and that matrix will be called non-singular. So if rank is equal to n, determinant will be non-zero, inverse will exist, such matrix is called non-singular. If rank is less than n, that matrix is called non-singular. Then it is called singular. If rank is less than n, then it is singular. So if A is singular, so are A multiplied by B and B multiplied by A. This will be singular and this will also be singular. So the statement proof of this statement, third statement, is also easier. So you will be required to do it at your home. And just before concluding, I write one more statement. Determinant of this product of two matrices, that is equal to determinant of this product BA, if these and that is also equal to determinant of A multiplied by determinant of B. We omit the proof of this last statement.